Number 65. Now we're getting into the vector fields. Calculate the curl of the vector field. Well, all right, that's pretty easy. Here's the formula. Kind of a plug and chug thing. It's a cross product type of formula. So let's see what we have. And okay. So the first, the I component is a little vector thing. It's supposed to be a vector arrow above that I. I don't know why that looks like that, but no harm. Curl is definitely a vector. And divergence, that we'll see next, is a scalar. So it's partial p with respect to y. So the terms go mnp. So 4z would have a y partial of 0. Minus n respect to z, the middle term 8yz. Partial respect to z would be 8y. And then move to the middle term. Partial of m with respect to z would be the first term. Respect to z would be 4xy. And then minus px, the last term, respect to x, would be 0 because there's no x. Come over to the k component. We have nx, partial of n, respect to x. Middle term, there is no x, so that'll be 0. And the last term, my, the first term, respect to y, would be 4xz minus that. So our curl is going to equal negative 8y, 4xy, and then negative 4xz. So sometimes these problems might ask for the curl at a given point. So then you would just plug in the x, y, and z numbers, and your curl vector would be numerical. But there it is. So that means that would be the curl vector for any point you chose. Divergence, scalar. It's this partial. It's mx plus ny plus pz. So that's easy enough. Once again, same order vector. It's mnp. So the x partial of this one would be 5yz. The middle partial respect to y would be 7z. And the last partial respect to z would be 4. And so it's 5yz plus 7z plus 4. Now it's interesting, look at answer choice B. They're trying to trick you here. They're writing it as a vector. But divergence is not a vector, it's a scalar, meaning it's just, in this case, algebra. So the same thing here is the last problem in the sense that if you plugged a number in, though, you wouldn't get a vector like you would with the curl. You'd plug some numbers in for x, y, and z, and you would get a numerical scalar answer. So don't be tricked by answer B here. Now we're checking to see if this function has a potential function. Now for a space vector, that means the curl vector field would be 0, 0, 0. In 2 dimensions, you use this rule right here. Partial my equals partial nx. If that's true, you have a potential function. And the potential function is the function f whose gradient is the vector field given in the problem. So if it doesn't check out that it has a potential function, then there's no function you can come up with whose gradient will equal the vector field. But if it does, then there is one. So partial m, first start here, respect to y would be negative 3. The partial of n, respect to x, would be negative 3. That means we've got one. So what we do is we integrate the first term with respect to x. That gives me 1/2 x squared minus 3xy plus 5x. Then you integrate the second one with respect to y. So you have minus 3xy plus 3y squared over 2 plus 7y right here. And then to combine this into a potential function, any terms that are the same term only have to be listed once, and then all loose terms are in there have to be part of the answer. So this, they're always going to share one term for sure. Sometimes it may only be that one term, but this one has a lot of loose terms to it, more than normal. Minus 3xy is common to both, so there's minus 3xy, and then every other term is in there somewhere. So obviously the order doesn't really matter other than it's just, you got to match the right answer. So I did write it out as in order of what the correct answer C looks like there, but there's no mathematical reason it has to be in that order. All right, so there we go. Line integral. Now, line integrals, of course, are done several ways. Depends on what kind of the equation you went. It's in this form. You have the differential form, and then you also have when they're vector fields, when you have to do f dot dr and that sort of thing. But when it's in this form, ds means integrating along the line segment s along that path. We have r here, so then there's the formula down here. You basically convert the function in terms of t by substituting, and then you multiply it by the magnitude of r prime. So r prime, so I just kind of consolidated the vector field, the path, the curve, parametric form of the curve. I wrote it in component form just to make it a little easier, and then to take the derivative. So it'd be -2, 2, and -1, taking them all with respect to t. So it makes that easy enough. So obviously, anytime you got a square root being a number, that helps us. So we plug that in. You're going to get square. You're going to get 4 plus 1. Square root of 9, which will be 3. So let's look at the first part. So you see for the x, I'm substituting -7 minus 2t. For the z, I'm substituting -t. And then the y squared here will be 2t quantity squared. And you can put this integral on the calculator if you'd like without having to do it manually. But we got to make sure we get it set up correctly here. So -7 times -t would be 7t. And then -2t times -t would be 2t squared. This one's going to be a 4t squared when you square it out. Add those together, you'll get a 6t squared. All right, so, and then we just integrate that. Basic antiderivative stuff here. 7/2 t squared plus 2t cubed with a 3 in front, going from 0 to 1. Plug that in there, and we get 33/2. Which is B. All right, I don't think that was too bad. Let's see what we have here, number 69. Work. Yeah, work is evaluating the line integral f dot dr. So we're going to have to do a dot product before we integrate. So here's r, t8, t7, t5. So the derivative of r prime then would be 8t7, 7t6, 5t4. And now we have to substitute to convert our force F into function of t. So x of t, y of t, z of t. So if it's y over z, it'll be t7 divided by t5. And then for the y term, it's x over z. So it'll be t8 divided by t5. And then for z, it's x over y, t of 8 over t of 7. So you get t squared, t cubed, and t. And then so we're going to dot these two items together right here. T squared, 8t7. T cubed, 7t6. T, 5t4. So you actually have two like terms here. You have an 8t to the 9th and a 7t to the 9th. So you add those together, you get 15t to the 9th. And then you'll have a 5t to the 5th, which naturally then doesn't combine. So to find this work, all I have to do is evaluate that integral, 15t9 plus 5t5 from 0 to 1. That's pretty easy. So the antiderivative basically would be 15t to the 10 over 10. That just reduces to 3/2. And then we have 5t to the 6 over 6. Put in 1, put in 0. We have 3/2 plus 5/6, which is 14/6, which then reduces to 7/3. right. Now, here's another one. Oh. Wait. The wrong way here. All right. Where are you? Here we go. Number 70. So there's the path for x, y, and z. That's the r, essentially. Those are r components. Now, don't forget the chain rule when you're taking these derivatives. That's very important, obviously. So the derivative of cosine of 2t is negative 2 sine of 2t. Then derivative sine of 2t will be 2 cos of 2t. A lot of people forget those 2's on the outside. Don't want to do that. And then the derivative of t is 1. So we have to then substitute to convert the force over to a function of t. So the first one's x times y. So it's just cos t times sine 2, cos 2t times sine 2t. Middle component's just 7. So the first one, the k will be 4x. So it'll be 4 cos 2t. So now I have to dot f with r prime, which dr and r prime, of course, are the same thing. So we have this times this right here, these two, will give me negative 2 sine squared t cos of 2t. 7 times 2 cos of t will be 14 cos of 2t. And then 4 cos 2t times 1 will just be 4 cos 2t. Now we have to, then see the last two terms are like terms, so they can be added together to make 18 cos of 2t. Now for this integral, we got to do a little u substitution here. We're going to pay attention to the half again here. So sine of 2t, the derivative, of course, will be 2 cos of 2t. Now, you could have pulled the 2 out. Since I just happened to coincidentally have a 2 there, I can let the 2 be represented right here. If not, I would have put a 1/2 here, would have pulled the 2 out, but the 2 still would have knocked out the 1/2 anyway. So you can let that 2 be this 2, and then you come over here and there's the negative sign. So the 2 is represented by the du, so it's just u squared du. Now I change the limits of integration. You put in pi over 4. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. And then sine of 0 will be 0. So this integral just becomes the negative of u squared from 0 to 1. Now the middle integral it's just taking basic antiderivative. Now I didn't show the work here, but I'll mention it verbally. So you would just the antiderivative of cos of 2t would be 1/2 sine of 2t, antiderivative. So that's what's turning the 18 into the 9 is the 1/2 that comes from this antiderivative. And there was no need to change limits or anything there. So I just left 0 in the pi over 4. So for the first integral, then I have negative u cubed over 3. This it looks like this one I didn't switch the order. It doesn't really matter, but earlier problems I was switching the limits of integration to get rid of that negative. But I kind of looked at it and saw it was going to be negative 1/3 anyway. Then over here, I plug in pi over 4. I get sine of pi over 2, which is 1. Sine of 0 is 0, so 9 times 1 is 9. And then 9 plus negative 1/3 equals 26 over 3. Let's see how we did here. There it is, 26 over 3. Number 71. Line integral that's written in differential form. So when it's in differential form, you don't have to do that square root thing. It's not in that ds form it gave earlier. So literally you just take y, then you'll take the derivative times the derivative of x, plus x times the derivative of y. And integrate it from there. Now I parameterized this one, so it wasn't already, notice it wasn't already parameterized, but it's easy enough to do. If you just let x equals t, that means y equals t cubed. So to convert this equation, y equals x cubed, over to parametric form, which we saw a long time ago, that's easy enough. Just make it t comma t cubed. And then the derivative dx and dy would be 1 and then 3t squared. So there's your dx and your dy. So then y will be t cubed, x will just be t. So we have t cubed times dx, which is 1. So you have t cubed times 1, plus x, which is t, right there, times dy, which is 3t squared. So I have t cubed plus 3t cubed makes 4t cubed. And then if x is going from 0 to 3, t is then going from 0 to 3 because t is x. So we're going from 0 to 3 of 4t cubed. Antiderivative of 4t cubed is t to the fourth. From 0 to 3, 3 to the fourth gives us 81. (72). This one, we have to parameterize it in two paths. It's telling you, see, it's telling you which way to go there. So we have to come up with two line integrals and add them together to get our result. If this was a conservative vector field, you could take any path to get there. So you could take one straight, one line to get there, but it's not, because my does not equal nx. My, remember that was back up here. Let me show you. Oh, there it is. Yeah, right here. My does not equal nx for that one because overshot it. There we go. My would be 3y squared, and x would be 2x. So naturally 3y squared does not equal 2x. So to parameterize this straight line down, we have okay, so we're heading a downward line segment. So the x is going to be constant at -6. So that'll be now the tricky part then is coming up with this. Now because we're heading downward, it's going to be -t, but then you got to figure out what number will make it fit. So there's probably more than one way to do this, but I always like to start with 0. That makes sense, start your integration at 0. So if I know it's -t, I've got to figure out then what would have to be, if that's -t, and I know I'm starting at -6, 1, it would be 1 minus t, put in 0, that would give me 1. Now you might think, why wouldn't t minus 1 work? Well, first of all, the t has got to be negative because you're heading downward. And second, you need a value for t that you can plug into this same variable and get to -4. So if you put in 0, 1 minus t, 1 minus 0 would be 1, and then 1 minus 5 would make it be -4. So that's how you take care of the y's that way. Then for your next path, you're starting at 5, because you have to start where you finished the last part. And I'm moving to the right, which means x would be a positive t. X stays positive, but y stays fixed at -4. So now I got to figure out t plus or minus. That means I know that when I put 5 into this value for t, I need it to equal -6, because we are starting at -6, -4. So it's kind of like saying t plus, some unknown x has to equal negative 11, so it have to be 5, I'm sorry. Negative 6 minus 5 equals negative 11. That's what I'm trying to say. So there's that. But anyway, you can double check, obviously. So then you put 5 in there. 5 minus 11 gives me negative 6. And then you can see that we're finishing at 0 for x. So now I know that t would finish at 11, because that would give me 11 minus 11, which would be 0. And so that's like I say, you can plug them in, check, and see where it ends up. That's probably the hardest part for the entire problem, is doing that, because now it's not too bad. So now I show we're doing y cubed dx plus x squared dy. First integral is going to go from 0 to 5. So that'll be 1 minus t cubed. And then the derivative of x is 0. So it actually wipes this part out. So it's already getting easier. And then x here is negative 6 squared times the derivative of 1 minus t, which would be negative 1. So now I come down to the one I labeled C2, the second path, the horizontal path. I'm going from 5 to 11. Now, of course, everything changes here because now y is negative 4. So it's negative 4 cubed times the derivative of t minus 11 dx would be 1. And then plus the x squared, which would be t minus 11 squared, times the derivative of y, negative 4, which would be 0. So that wipes this out. So this just became super duper easy here. So we're just integrating a couple of numbers. So you have negative 36 dt from 0 to 5, and then negative 64 dt from 5 to 11. And that worked out pretty easy. So yeah, the setting that thing up was the real challenge. Ends up being negative 564, which is answer C. All right, problem number 73 is the evaluation of a line integral with limits. And as I mentioned in this note here, since the integral is written with limits, that means the fundamental theorem of line integrals definitely applies. So the vector field is going to be conservative. You don't have to even check that. And so what we can do, the best way to do this, obviously one way to do this is come up with a parameterization between these points, plug in all the t's and do all that. But actually using the fundamental theorem of line integrals I think would be a bit easier, which means we know there's going to be a conservative function. So you integrate the first part with respect to x, and you'll get x squared y squared minus x squared z squared. Integrate the middle part with respect to y. So 2x squared y becomes x squared y squared. And integrate the last part with respect to z. And you'll have, so the negative comes with it, so negative x squared z squared. And then we combine, remember the idea is that all functions, whatever common terms belong in there only once. And then any loose terms also come along. So there's 2 negative x squared z squareds, and there's 2x squared y squared, so there really are no individual loose terms. So our potential function then is just x squared y squared minus x squared z squared. And then once you have the potential function, in terms of x, y, and z, you just literally plug in these points, these limits of integration, plug in the lower, plug in the upper, subtract just like you would using the fundamental theorem of calculus, and you plug it in there. Pretty easy number calculation. You get negative 495. So like I said a few minutes ago, that otherwise you have to parameterize these 2 points, which isn't that hard. R of t would just be 3t, 3t, and 8t. And t would go from 0 to 1, but then you got to plug in all that and do all that mess. And I think this is much quicker. It's not that that's that hard, but much more efficient. But anyway, if you want to do it that way, that's fine. Here's another one. So you see, using the fundamental theorem of line integrals, I didn't even verify that it was conservative, because it is. So when you integrate both these functions, they're u subs, they produce the exact same term. So therefore, that's the common term. And f of xy is just negative 1 over 4 times x to the fourth, y to the fourth. So now you can plug in the upper point, which is 4, 4. Plug in the lower point, 1, 0. Now I reversed them so I can get rid of the negative. That's the only reason. If not, don't worry about it. You don't have to do that. And then I got 1/4 times 1 minus 1 over 5/12. It ends up being 5/11 over 2048. Answer A. I don't know why I have some of these answers circled and some don't. The original version without the worked out solutions, at the end of it has the correct letters for each answer. The key is on there. But I'm not sure why I don't have all these circled here, but that's okay. I might go back and fix that later, but not in the video. All right, Green's theorem. Here it is. So to evaluate the line integral in differential form, you evaluate it as the double integral of partial nx minus partial my. Something's off with my fonts here. I should redo that. That double integral is so much smaller than these. Okay, well, that's all right. But that comes in real handy in situations like this when you have parameterizations that take on different paths. So doing a double integral across an area region would certainly be much more efficient. I mean, you could do this as 3 line integrals added together. In other words, you could start at 0, 0 and go to 3, 0, and then 3, 0 to 0, 3, and then 0, 3 back down to 0, 0, and add those 3 together, and that would work. But this is just so much more efficient to use Green's theorem. So here's the nx goes first, so the derivative of 6xy with respect to y will go first, so it'll be 6x. And then we have x minus 2y, which is the m, with respect to y would be negative 2. But you see the formula has a minus in it, so basically 6y minus a minus 2 is the same thing as 6y plus 2. And so we'll just work this out. First antiderivative, respect to y, would make this 3y squared plus 2y. We evaluate this as 3 minus x to 0. Oh, because the region, yeah, let me explain that. So you have so you have the line y equals 3 minus x, is that slanted line. So if you go dy dx, it would be from 0 to the line 3 minus x, and then your left or right would be from 0 to 3. Because remember, the outside always has to be numerical. Sometimes, you know, when you have circular regions, you'll be doing these as you would do them as polar integrals. So let's see. Okay, you see we have 3 times 3 minus x squared plus 2 times 3 minus x. I'm not going to go through explain all the algebra here, but if you square the binomial, distribute, combine the terms, you should end up with this right here. 3x squared minus 20 plus 33. And then we take the antiderivative of that and evaluate it at 3 and 0. So 3x squared antiderivative is x cubed. Minus 20x would be negative 10x squared. 33 would be 33x. Put in 3, put in 0. 0 will be 0 here. But you put in 3, you'll get 27 minus 90 plus 99, which equals 36. And there we have it. Yeah, I think there were some problems when I was doing the line integrals. Probably not in the Green's interval section. I can't remember where it was, but, I took something and did it the longer way on purpose. Not that we had to. But might have been in the the fundamental theorem of line integrals, where I did multiple paths and added them together and showed it equaled. If you go back and have a look at that, you would see that, makes that a lot more tedious, and you'd rather do it this way. Even though mathematically it would not be hard to calculate the line integrals, but the setting up of the RT can be challenging, as we saw in an earlier problem that I did on a different video. Let's see. Here's another Green's theorem. Okay, this is circular, XY plane, oriented counterclockwise. They're just mentioning that because one of the definitions of the theorem behind Green's theorem is that the area needs to be on your left as you're going. So, not that big of a deal, really, but that means that's why I was explaining earlier, if you did these as individual paths, you'd have to go left to right, go up, and then down. That doesn't matter. That's kind of the reason why it's mentioned. So we have x cubed minus 4 sine y, so I need to take the x partial of that, which will just be 3x squared, and then take the y partial of ex minus 3y squared, y cubed, excuse me, negative. So the derivative of negative 3y cubed would be negative 3y squared. So 3x squared minus minus makes that 3x squared plus 3y squared. Well, that works out kind of handy. Oh, and here's a mistake right here. I don't have it, I've calculated it correctly, but, well, let me see if I can do this. I'm not using a tablet PC, so I'm kind of having to do this freehand on a mouse pad. I can't write it, so, but that should be 3r squared. Oh, let's see if I can do that. And if you look at the next line, which I'll go to in just a second, I have it written properly there. I just don't here. All right. So I guess I need to repost that. Well, show that for now. I'll probably rewrite it by hand, maybe before I post it, or maybe not. That's probably okay. So that's 3r squared, and we already have a circular region of integration anyway, so this was going to be polar pretty much no matter what. So, and there's nothing in the problem indicating restrictions for x and y being positive, greater than or equal to 0. So you can assume it's the entire circle. So it's radius 1. So it goes from 0 to 1. And then 0 to 2 pi around the entire circle. So that part becomes 3r squared, and then you automatically have the r here, of course, r dr d theta. So you're actually integrating 3r cubed when you multiply them together. So antiderivative of r cubed is 1/4 r to the 4th, so the 3 over the 4 are just brought to the outside. So you have r 4th, 1 and 0, just going to make that a 1, that's just going to go away. And then now you're left with 3/4, 0 to 2 pi d theta. So it's 3/4 theta, put in the 2 pi, 2 over 4 puts a 2 on the bottom, so it equals 3/2 pi. Let's see if that's, oh, that one was not a multiple choice, okay. Question. So let's see what we have here. The divergence theorem is we take the divergence and we integrate it across the triple integral region, dv. So let's see what we have here. So the divergence be the x partial of 3x y squared makes 3y squared. 3x squared y, the y partial of that would be 3x squared. And then the z partial, the last term, would be 0 because there's no z term there. So this is the basic setup, what we're integrating, dv. Now this one won't be too bad. Everything's going to be numerical. That's going to make it easy. And we're going to go ahead and go polar. Polar is going to work best here, well, because the region is a cylinder for the base. and then your height's just two flat planes. So it's a cylinder starting on the XY plane and stopping with a horizontal plane of z equals 6. So that means actually everything's numerical here. So of course 3y squared plus 3x squared is the same thing as 3r squared. So we'll go from 0 to 6, and then we have 3r squared r dz dr d theta. And then inside the entire cylinder, which is a circle on the xy plane, 0 to 3, and then 0 to 2 pi. So we have to just work this out. Now the first integral, we don't, unlike the last problem where it was a double integral just using r, is it's dz, so we drop a z in there. So z comes down, 6 minus 0, so that's just going to throw a 6 in there. Oh, went too far there. So let's see. So the 18 comes from, a 6 comes in for the z times that 3 is 18 on the outside. And then we have now we take the antiderivative of r cubed, integral of r cubed with respect to r. So that's 1/4 r to the 4th, put in 3, put in 0. And 18 times 1/4 is 9/2. 3 to the 4 is 81. So you have 9/2 times 81, 0 to 2 pi for d theta. And then that just puts a 2 theta in there. So 9 over 2 times 81 times 2. You see the 2's would cancel, of course. And that's going to give you 729 pi. There we go. All right. Stokes Theorem. We integrate the curl dotted with the normal vector. And the normal vector is going to be negative zx, negative zy, and 1. A lot of these problems in this material produces a lot of zeros for the curl vector, which certainly doesn't hurt my feelings by any means, but the curl's pretty straightforward. So partial of p, the last term, respect to y, 5z cubed has no y, so there's a 0. nz, the middle term has no z, that's a 0. mz, first term has no z, so that's a 0. px, last term has no x, so that's a 0. Next one, nx, the middle term, finally got something. That derivative of 2x will be 2, minus my, first term, that will be 6. So your curl vector is just going to be 0, 0, negative 4. Now to get your z, you just take the equation of the plane, solve for z in terms of x and y. So we're going to have some fractions down here. So then when you divide by, so obviously the first, it's going to be 9z equals, up here, 8 minus 6y minus 6x. Then I just divided by 9. And so the negative, so that's a negative term right there. So the negative zx partial will be negative of a negative, which will be positive. And then I just reduce, well, there I wrote the two partials right here. So that was probably more efficient. There they are, reduced. So it's negative 6, 9. Both of them are negative 6 over 9. So they reduce to negative 2 over 3. So the negative in the normal vector makes it 2/3, 2/3, and 1. So all we have to do is dot the curl with the normal vector, and we get negative 4. So this is actually a double integral for this theorem across dy dx. So all we're integrating here is negative dy dx. So you see that the plane equation, just take out the z. Z is, because we're in the xy plane, so which means z is 0. So we're just working with 6x plus 6y equals 8. Now, it's really not going to matter from a difficulty standpoint whether you choose to go dy dx or dy or dx dy. Not at all. So I just went dy dx because that's if there's no difference, I generally will go dy dx most of the time. So we take the 6y right over here and solve for y. So you get 1/6 times 8 minus 6x. And let's see what we have. So the inside limits of integration for dy will go from 0 to 1/6 times 8 minus 6x. And then when you get to dx, that means y will be 0. So you're essentially solving this equation, 6x equals 8. 8 divided by 6 is 4/3. So the outer limit would be 0 to 4/3. So this cleans up kind of nicely there. I went ahead and just brought the -4 out. So when you integrate dy, that's just going to be y, which will just bring down this upper limit right here. So the -4 on the outside with the 1/6 will combine to be -2/3. And then the antiderivative of 8 will be 8x. Antiderivative of minus 6x will be -3x squared. So once again, and once you get down to the last integral, if you want to do it in your calculator, the f and int function, that's fine. But obviously you got to get down to that final integral. Put in the 4/3, put in the zeros. So here I just wrote the 4/3 out. So obviously use a calculator for that. Even if you want to work it out, still use a calculator here. I didn't show a lot of work there, but it does end up being -32/3, which should have been one of the answers. Wait. Let's see. Okay, I paused the video for a minute because it wasn't matching the answer, so I don't know. So I put it in the calculator just to verify, and I must have just, I don't know if I had just some sort of brain fart here or something, and I don't know why I wrote 3 unless there's something wrong. I didn't check what this part, but I can go back and check that later and see if there's a mistake. Maybe I just typed something in wrong. It'd be 8 times 4/3 minus 3 times 4/3 squared. So I don't know if this part produces -32/3 or not, or I just wrote it down wrong. But there you see, there's the integral set up right here. Well, there's the -2/3, and there's the 8 minus 6x from 0 to 4/3. So I'm convinced that the -32/9 is correct, and I just wrote something down wrong. I don't think there was anything wrong with the process. Now these last two, to prepare for the final, I did not have those earlier in the review. Obviously, this was not the last thing we covered in the course. This was back in the chapter that included the partial derivatives and all that kind of stuff. In fact, it was right after partial derivatives. But instead of just restructuring the entire review, reorganizing and all the solutions and everything, I decided to tack these two problems on at the end. Make it a little easier. And total differential, and then the exact change in value. So to find this delta z, there's two things we want, delta z and dz. Delta z, and it's easy to use your calculator for this, delta z literally is taking the function value at this second point, p to q, so from p to q. So it's second point minus first point. So all you do is literally plug in 1.01 and 0.99 in for x and y, minus plug in 1 and 1 for x and y, and you subtract. So it looks like I did that second. See, there it is. Oh, okay, I can jump back, but let's see. It's sometimes people make this harder than it needs to be, but it's really actually not difficult. So you see, I put in the first point minus the second point. Just crank it out in the calculator, 0.392. So we know that obviously, look at, I don't think your answers on the exam would have this many decimal places, but it's kind of interesting. But that's all right. We'll be able to take care of it. But let's look at what the dz, the actual differential, is. Because the whole idea on this, just a quick reminder, is that the dz is supposed to be an approximation to the delta z. So that's all. So it should be, the answer should be close. dz and delta z should be fairly close to each other. So this is here's the formula for the dz. It's fx dx plus fy dy. Now, if you had because sometimes it might be w as a function of x, y, and z, so it might say dw, then you would have a plus fz dz. I don't think you have to worry about that too much, but I think that's in my notes for that section. And I'm not sure what... you would have done this problem on exam too. Should have had something like this. Well, anyway, so you take the fx partial. That's easy enough for this one. 4x cubed y squared will be 12x squared y squared. And then the fy partial would be derivative 2 y squared would be 2y, so it makes it 8x cubed y. And dx, what dx and dy represent, they represent the change in x and the change in y, which either one of them, they could be positive, they could be negative, they could be zero, but you essentially, so to find dx, you take the second x point minus the first x point. So 1.01 minus 1 would be positive 0.01, but the next one's going to be 0.99 minus 1, which will be negative 0.01. So that one's going to be negative because y decreased. Okay, so then that's what we plug in here. So you see the dx is 0.01, dy is negative 0.01, and the xy that you plug into the equation here, because there's 2 points, how do you know which one's which? It's always your starting point from P to Q. So the P represents the x and y that go in there for that equation. It's always the first one. So you plug in 1 and 1 here. So that makes that easy too. So it's 12 times 1 squared times 1 squared times the dx, which is 0.01, plus 8 times 1 cubed times 1 times negative 0.01. And that ends up being 0.04. So you can see that it is, didn't circle the answer, but 0.04, then 0.392. It's answer A, because 0.0392 was the answer below that I actually did first. So let's take a look at one more of these. I did not put any, since these problems don't have applications, which you might have had on your second exam, that means there won't be one on the final. It means it would be just like this. But you can, use these to sort of represent, measurement errors and things like that. That's kind of the application. You may recall it from Cal 1. If you don't, that's okay. But of course, we didn't have a third variable there in Cal 1, so. All right, same principle. Now I've kind of explained the principle. We can go through this one probably a little bit quicker. So the x partial will be 2x and then plus y. And then dx will be 2.02 minus 2. So it's 0.02. The y partial will be xy will be x. And then minus a y squared will be minus 2y. So it's x minus 2y. The dy will be 1.97 minus 2 is negative 0.03. And then we use 2 as our point that we plug in for x and y. So there's the differential equation again. The total differentials, fx dx plus fy dy. So fx put in, so it's 2 times 2 plus 2. I guess just coincidence, both problems in a row, that the x and y had the same numerical value. Obviously, you don't want to make that as an assumption or anything, but and then times the dx, which is 0.02, plus 2 minus 2 times 2, times dy, which is negative 0.03. I got 0.18 for that. And let's see what we have for the differential, which is literally f of the second point minus f of the first point. So you're not using the partial derivatives at all. You're literally putting, I'll scroll back up here, you're putting 2.02 and 1.97 into this equation for x and y. Then you're putting in 2 and 2 into that same equation, and then you subtract. So you see I wrote all that out, 2.02 squared plus 2.02 times 1.97 minus 1.97 squared, and then 2 squared plus 2 times 2 minus 2 squared, and I got 0.1789 roughly. And you can see that those are pretty close to each other. Let's check the answers. And it would be answer A. Well, all right, that concludes, that's the last problem for this review.